So in this example, we're going to be stating the domain and range of the function f of x equal to -2 times the square root of the sum of x plus 1. And then on the outside of our square root, we have plus 3. Now to do this, there's a couple ways we can approach it. I'm just going to approach it by using the transformations, applying it to the parent function's domain and range. So the parent function of this function is the square root function, the square root of x. And the square root of x normally has a domain of x being greater than or equal to 0. And it normally has a range of y greater than or equal to 0. If I use the rules I use for transformations throughout all the different lessons I do, inside stuff affects x, but in the opposite way. So I see x plus 1. So what's really going to happen to x is we're going to take the x values and subtract 1. The outside stuff affects y, and in the same way. So we have this -2 connected by multiplication, and this plus 3 connected by addition. So we're going to take our y values, we'll multiply by -2, and then we'll add 3. Now I just have to apply that to the original parent function's domain and range, and that will actually change it to this function, f of x's domain and range. So for my x values, I'm going to subtract 1 from my x values. So 0 minus 1 is -1. So x greater than or equal to -1. Number of other ways we could actually write the domain, including the interval notation. So from -1 to infinity with the interval notation. For the range, we are going to do two things. So we're going to multiply by -2 first. So when we do 0 times -2, now that doesn't actually change. Like 0 times -2 is still 0. However, anytime you multiply by negative for inequalities, you have to flip that inequality sign. So now, instead of greater than or equal to 0, it's going to be less than or equal to 0. But we're not done with our transformations, so the number's not going to stay 0. So after multiplying by -2, 0 times -2 is still 0, but then we have to add 3, so 0 plus 3 is 3. So overall, I can figure out kind of where my graph is going to be. I know it's going to be greater than -1 and less than 3, so it's probably going to be something like that, less than or equal to 3. So general shape wise for my graph. But again, we can also write this in different forms, such as the interval notation, which I'm doing it backwards this time, from -infinity to 3. And there we have it. Okay, our second example here, we have the equation -2 times the square root of x plus 1, and then on the outside, the plus 3. This is the same equation we looked at in the first example. But going through, so to graph it, we're going to still use our transformations. Inside x opposite, so we're going to have x minus 1, and outside y same, so we're going to have y times -2, and then plus 3. Now with this, we're going to need some points to kind of help us out. The basic graph of a square root function we have up here. So here's the general shape of the square root function. Normally, I use the points, the x values -1, 1, and 0, but in the parent function square root of x, the x value of -1 doesn't exist, so I can't use that as one of my key points to help me graph it. So instead, I'll use the point 4, 2 to help me get the shape and stuff correct. So I'm going to use these 3 points here, which is part of the parent function, the square root of x function. I'll use them to help me graph the transformed function. So with that, the points that we're going to use for the square root of x are 0, 0, 1, 1, and 4, 2. Just like all the other units I've done, I'm going to go through and change all the x values first, and then I'll go back and change the y values. So my x rule is to subtract 1 from x values. So 0 minus 1 is negative 1, 1 minus 1 is 0, and 4 minus 1 is 3. Then I'm going to go back and change all the y values. We're going to multiply by negative 2 and then add 3. 0 times negative 2 is still 0, plus 3 is 3. 1 times negative 2 is negative 2, plus 3 is 1. And 2 times negative 2 is negative 4, plus 3 is negative 1. So there are my new points for this transformed function. Negative 1, 3, 0, 1, and 3, negative 1. Now to make sure I get the shape as I draw this correctly, I'm going to scroll back up to the original graph. You'll notice the original graph starts at the point 0, 0 and kind of curves through the other 2 points. So when I draw this in, I'm going to start at 0, 0 became negative 1, 3. So I'll start at negative 1, 3, which is that point I highlighted there. I'm going to curve through and off the side of the graph. So it's going to look something like this. It may not be 100% accurate since I'm drawing it by hand, but that's more or less what it will look like. And there we go. You can also describe transformations as a reminder. Addition, subtraction is translation, so we can tell that it's been translated. 1 left and 3 up. It's also been reflected because of the multiplying by negative, and dilated because we multiplied by 2. Just as a reminder. Okay, in this example, we're going to be graphing the function, the cube root of the difference of x minus 2. And then on the outside of the cubed root, we have a minus 1. So now this is a cubed root function, but I'm going to do the same thing. I'm going to use transformations to graph it since x only occurs 1 time. Inside I see x minus 2, so inside x opposite, so we will do x plus 2. Outside y, same. Well, I technically see 2 numbers on the outside. I see the 3 for the index and the minus 1 off to the side. However, the 3 for the index just tells us what type of function it is, so it tells us the basic shape. So all I have to worry about for transformations is the minus 1. Now this one's a cube root function, so if I scroll up quickly here, you can see off to this side, we have the cube root function. The cube root function looks a little bit different from the square root function, similar to how quadratic functions look different from square root functions, even though they are related. This is very similar to the x cubed function, which looked like that. Now the 3 points we're going to be using is negative 1, 0, 0, and 1, 1, just to help us get a little bit of better shape. Those are the 3 reference points we're going to use. They come from just basically using the parent function, doing the cube root of each of these x values, which are the same x values I've used in most of the lessons. An exception, though, would be the square root, because we can't actually square root negative 1. But cube rooting will give us the y values for each of those points for the very basic parent function. So if I go back down, for the cube root parent function points, I'm going to be using negative 1, 0, 0, and 1, 1. Just like all the other times I do transformations, I'm going to start with the x stuff and change that. I'm going to add 2 to my x values. Negative 1 plus 2 is positive 1. 0 plus 2 is 2. And 1 plus 2 is 3. I meant to keep it color-coded, but I kind of failed at that this time. But we'll do the y rule now. Our y is minus 1, so negative 1 minus 1 is negative 2. 0 minus 1 is negative 1. And 1 minus 1 is 0. We'll go ahead and plot each of those points. 1, negative 2. 2, negative 1. And 3, 0. For the shape to draw this through, the shape of the cube root function, I like to think of it as an S that's been kind of pulled out this way and out this way so that the middle part almost becomes flat. That's kind of how I look at this shape whenever I try to draw it. I find it makes it a little bit easier to try to draw it. It is a tricky shape to try to draw for most people. A lot of the times it comes off looking very funny when you're trying to sketch graphs of these. But there we go. Now, in this last example, we're asked how can we rewrite the following radical function to identify the transformations, specifically the translations and reflections, or the translations and dilations from the parent function f of x equals the square root of x. Now, a lot of the times, most of our functions can be rewritten so that there is no horizontal dilation or no multiplication on the inside of the function directly to the x values. So a lot of the times you won't see that. There are some rare cases. For instance, these ones, you can't actually rewrite ones where there's a negative beside the x, just because of the imaginary number issues that happens with that. But it does create reflections still. Now, if it is not a reflection, though, you can rewrite it. So this one doesn't have a reflection there. So I would be able to rewrite this so that we don't have to look at a horizontal dilation, which is a little bit different from most of the problems that we've done all year. To rewrite this, we want to start by factoring out whatever the coefficient is with x, no matter what it is. So we're going to factor that out of both terms inside the radical. So if we do that, we will end up with 4 times, in parentheses, x plus 4. 16 divided by 4 is 4. My plus 7 isn't changing. Now, one of the properties of radicals says that if you have two things connected by multiplication inside the radical, we can separate them into two separate radicals. Since the 4 and the x plus 4 are now just connected by multiplication, we can separate them into two separate radicals. We could not do that before because even though there was multiplication here, that particular set of multiplication was connected to something else by addition. Whereas in the current version of this, the addition is on the inside and the addition would be done first before the multiplication. So this addition is kind of separate from the multiplication. The addition has to happen before that multiplication. And that whole binomial is now only connected by multiplication to the 4, allowing us to separate it here. My plus 7 is just going to kind of come down for the ride here. And then we can actually do the square root of 4. The square root of 4 is 2, so it ends up simplifying or being rewritten into 2 square roots of x plus 4 plus 7. So we can rewrite it in this fashion. Now we can identify the transformations a little bit easier and talk about vertical dilations rather than trying to do horizontal dilations, which can get a little bit messy. We have the vertical dilation of dilated, in this case, stretched, vertically, by a factor of 2. And inside x opposite means we're going to be translating left 4 and up 7. And there we have it. Okay, so in this one, we have f of x equals the square root of 4 minus 2x underneath the radical, and the plus 1 after. Now with this, since we're trying to graph it, we could try rewriting it by factoring out stuff. However, because of my negative in there, I'm not going to be able to completely rewrite it without horizontal multiplication transformations happening. So we're not going to worry about rewriting it. Instead, we're going to just go for the transformations as is. So normally we do inside x opposite, and we're going to still do that. So we see we're technically adding 4 because it is a positive 4 connected by addition, and we're multiplying by negative 2. Which means, since it's inside x opposite, we're going to be subtracting 4. We're going to be dividing by negative 2 inside x opposite. But it is important which order you do things in. Well, again, inside x opposite affects in the opposite way. So normally, the order of operations is the normal method. So since we are doing opposite for the stuff that affects x, we would start with the addition subtraction stuff. So x is going to be subtracted by 4. And then that result will then be divided by negative 2. And that's the transformation rule for the square root function. And then for the outside stuff, I just have the plus 1. That's the same as normal y plus 1. Now we'll just take some ordered pairs, key reference points that we can use from the square root function, which I talked about earlier. So 0, 0, 1, 1, and I'll also use 4, 2 to help us get a better picture of the shape. We'll apply the x rules to each of my points. So we're going to take our x values, subtract 4, and then divide by negative 2. So 0 minus 4 is negative 4. Divide by negative 2 is positive 2. 1 minus 4. Well, 1 minus 4 is negative 3, and negative 3 divided by 2 is negative 3 halves, or negative 1.5 I find nicer when we're trying to graph. Then for the last one, 4. 4 minus 4 is 0, and 0 divided by negative 2 is still 0. For my y rule, we're going to add 1. So 0 plus 1 is 1. 1 plus 1 is 2. And 2 plus 1 is 3. We're going to go ahead and plot each of those points. 2, 1. Negative 1.5, 2. Negative 1.5, 2. And then we also have 0, 3. I think I made a boo-boo. Yep, I made a boo-boo there because I was dividing by negative 2 right here. So that should be positive 1.5 because it was 1 minus 4, which is negative 3, and then negative 3 divided by negative 2 is positive 1.5. So I knew something was wrong because the points were not in the correct order there. So 1.5, 2, and then 0, 3. Again, we're going to start at the point that was originally 0, 0, and then curve through the other points. So we're going to start at 2, 1, and then we're going to curve back through the other points and off the side of the graph. So there we go. So you can see that it's been reflected horizontally across the y-axis and then slid over to the right and up for the transformations.